So my assignment was big data, storing, moving, mining, visualizing, things HiPACC could be leveraging. So moving, I want to talk about Scenics, upgrade to 100 gig. Storing, talk about our data oasis, storage infrastructure at SDSC. Mining, talking about a little bit about our supercomputers, Gordon, which is operational now, Comet, which will be operational by early next year. Visualizing, YT. I won't talk about YT, I'll just point to it and say you've heard about that. And then sharing, talk about this new software as a service thing that we're developing at SDSC called seedme.org. Okay, Scenic. So the high-speed networking in California is done by Scenic. It is probably the best big data optical network in the nation. 3,800 miles of optical fiber. It connects everything. All the universities, all the, that's not just the research universities, but the state universities, the community colleges, all the schools, everything. And it has different segments, and one of them is the research and education segment, which is being upgraded to 100 gig right now. In fact, it's already done. It's a level 2 service, if that means anything to you networking people. So Scenic is connected to Internet 2, which partnered with ESNet a few years ago to upgrade the national networking infrastructure to 100 gigs. So that's a done deal. That was done with Recovery Act money. Scenic is now putting their money in. Scenic is upgrading the statewide research backbone to 100G. Oops. That's out of order. Fat finger error. Okay. Okay, but that's like having an interstate freeway with no on-ramps or off-ramps. So the issue is campuses connecting to this. And I want to tell you two things. One is UCSD will be connected to Scenic at 100 gig by the end of this year. This is a project funded by the National Science Foundation through a program called CCNIE. And basically, this program just buys networking gear for campuses to upgrade their networking infrastructures. And many campuses, I mean, this is the way research universities get their money for networking hardware. And it's of two kinds. One is what's called the edge, which connects to the wide area network. And this project will upgrade our edge switch and router to 100 gig. But then there's what's called campus distribution. CCNIE funds both of these kinds of grants, and they just throw out the money year after year. And so what you're going to see is within a year or two, all the UC campuses will be at 100 gig, both at the edge and on the campus. So that's point number one. Right. So that's your problem. That's the campus problem. It's separation of concerns. Yeah. But I'm saying this is a resource that will be available to the UC system. And these are the UC campuses that are getting these CCNIE grants in addition to us. You got one in Santa Cruz. So see, UCLA is there now. Okay. Santa Cruz is going to be connected. In this latest round of CCNIE grants that funded me, there's also UC Davis and UC Berkeley. Now, so that's think of that as the Internet 2 part. But the other point I wanted to make is that my center at SDSC will be connected at 100 gig two different ways. One is via ESNet, and the other is via CNIC, which connects to Internet 2. So because half of the HiPACC action is all ESNet world, that makes SDSC a very interesting place as a node in, something bigger and cooler for HiPACC to do. We have application drivers in my Cherub proposal, one of which is Polar Bear, which will be upgraded and sending more data down. Of course, the data arrives at Berkeley first, and then some data will come down to UCSD for processing. So that was the first point. The networking is about to get a serious upgrade. The second, I wanted to talk about what a data-intensive supercomputer center looks like, according to us. Now, everyone does it differently, but this is just what we've done. And it's a weird, inside-out view of computing. This is a diagram of what we call the data oasis system at SDSC. That is our Lustre parallel file system that is mounted by 3 different HPC clusters. And this thing doesn't work anymore. Is this? Okay. So here's the Gordon system. There's 2 other clusters. Here is 4.5 petabytes of Lustre file system. But the most important thing in the whole diagram are these 2 switches. So for a data-intensive supercomputer center, everything's a peripheral to the switches. And so each one of these switches has 3.8 terabits bandwidth. And we have 2 of them for redundancy. And so what these are 10 gig switches with 384 ports. And so, for example, Gordon has 128 of those to sustain 100 gigabytes per second through to Gordon. But other cluster, everything is connected to these switches. And so, for example, let me just make the point that you can write an exceed proposal for a storage allocation on the Oasis project partition, and that can be persistent, right? So HiPACC could write a proposal and get a big block of storage, and it could be there as long as you are doing good science and writing renewal proposals. So that's point number 1. Point number 2 is this 100 gig connection comes in to these Arista switches. This is what we have now. We are upgrading the Aristas to 40 gig technology. And so with the 40 gig fundamental links, we'll be able to increase bandwidths to Data Oasis in the future. The other point is that we have built a cloud at SDSC. This is an OpenStack compute and object store cloud. And that is connected in through these switches. So the way I think about it is this is a data infrastructure. Data could be coming in from, outside over the national network or even international, flows in here. Where does it want to go? It can go here for processing. It can go here for storage. It's here for storage. You work on it. You produce data products. You can push those out to the cloud for access for the community. So this is the way we think about building a dual-use high-performance computing center for both computational science and data science. So, all right, so now I've said this is all based on OpenStack, a Swift object store plus Nova Compute. And the way I think about this is a platform where communities can build their HPC-connected data services. We call it data as a service. So that is the strategy of our cloud group. We have a group that is devoted to this. And data as a service is our guiding light. But we see that cloud as being connected to other resources. Think of the cloud as kind of an endpoint in a workflow. Okay, let's go to point 3, which is the data mining. Gordon is our current data-intensive supercomputer. It's been in operation for almost 2 years now. It was the first HPC system, at least in the open, that had flash in its memory hierarchy, 300 terabytes of enterprise quality flash. But the other thing about Gordon is all the I/O channels are maxed out. You know, when we designed the thing, we just bought the fastest parts we could find. And CPU speed was the last thing we worried about. That's not what we're about. So everything is maxed out. I/O from the file system, I/O through the InfiniBand, which was dual rail to double speeds. I/O, you know, from the memory subsystems of the Sandy Bridge microprocessors to the cores. At the time, when we wrote the proposal, 2009, that was the best you could do. Now, one of the things we've done subsequently, which is really cool, is that we can spin up an SSD-based Hadoop cluster from our batch scheduler. So person X can say, give me a Hadoop cluster, and it needs to be this big. You just submit a batch job. Gets spun up. The temporary storage is on our flash, which makes it very fast, because that's IB connected to our processors. You load your data from Data Oasis, you do your science, you bust it down, you know? So it's basically Hadoop on demand. And we can support multiple of these, just depending upon what's in the queue. This computer, which I think was really a pathfinder, I think we actually beat the DOE labs here, is a forerunner to the Catalyst system. Catalyst is a new data-intensive system that they operate at Livermore. And gosh, doesn't it look just like Gordon? Well, in fact, it is Gordon. It's just that Appro got bought by Cray, and so the name changed from Appro to Cray. But you can see it's the same hardware. There's some slight differences in the Catalyst architecture relative to Gordon. Huh? The color is different. The photographer wasn't as good. So Gordon is going to last forever. We have a new supercomputer coming called Comet, which was half of a far more comprehensive computing environment, but the NSF didn't fund the other half. But it's not a bad thing. It's going to be a cluster based on Haswell microprocessors. It will have 128 gigabytes per standard node. It'll be about 2 petaflop system. And again, you see the computer is off to the side because it is really a peripheral to the switch. And the switch talks to the computer, and it talks to our Data Oasis. So what we're going to do is we're going to get whole new gear for Data Oasis. This is going to be the latest, best disk technology. It'll be 7 petabytes. It will sustain 200 gigabytes per second. And it will be 40 gig connected to the Arista switch, connected to the computer. But then we're going to take our existing Data Oasis, move it over, and make it a second copy store. Because if you get into the data business, you've got to have replication. Otherwise, you just, you're not credible as a place that's serious about their data. So we'll have 4.5 petabytes of replicated storage. Also at, a Lustre file system available at high speed. This will be connected to Internet 2, ESNet at 100 gig. And we envision this cluster as supporting workflows. So the other unique thing about this system is it will be the first virtualized HPC system. We will virtualize not only single nodes, but clusters. So you'll be able to spin up a cluster, and because of some new networking technology called SRIOV, there will be no performance penalty for virtualizing it, because the I/O has now been virtualized thanks to Mellanox. So we will be able to support virtualized clusters for individuals and communities. But we're really targeting communities of practice who will then build their custom software environment inside these virtual containers. And that will play very nicely with data-intensive workflows. The other thing that we've done about the cluster itself is it is mostly standard compute nodes, but we have some fat memory nodes. We have 72 Kepler-3 GPU nodes. It's a Swiss Army knife approach because if you look at real data science workflows, they're multi-stage, they're heterogeneous, and you want to place things where they work best. So, and by the way, the standard nodes will all have flash on them. So that was the lesson learned from Gordon, is local storage is incredibly useful. So I think that'll be a nice machine for both HPC and data-intensive science. Now, I would say that Gordon presaged what the big dollar DOE labs are now doing. These are two slides that I've taken from the Comp Division review that I was on a month ago at Livermore. So these are slides from Disipinski, who is their CTO. And so the future systems that they're looking at will include multi-level memories. And so you could think of Gordon with its CPU, with its RAM, and then its flash as a first instance of a multi-level memory system. But the NVRAM part is going to evolve rapidly because of technologies. And so what they're looking at quite generically is you've got your cores and their local caches, and you've got your DRAM, but there will be a second level of memory that will be some NVRAM technology, probably not flash, probably phase change memory or something else, memristor. And the idea is that this first level of memory is fast memory for high bandwidth access, and the second level is slow memory, high capacity. So I think the way that I interpret this is the way that the DOE exascale projects are envisioning accommodating this dual use requirement that's being imposed by Congress on doing both high-end simulation and high-end data analysis. That's the first thing there. And then the second, this is another slide that I've taken from that review, talking about their burst buffer concept, which we heard earlier today, which is, was a concept introduced by the Gordon system. It was flash. And so what I'm seeing is that the architecture of the future is going to be good for simulating and data analysis, in the sense that there's going to be the possibility of having large amounts of data close to processors for in situ processing and, inline processing of simulation data. And that takes us to the next topic, which is visualizing. Well, YT is, emerging as a nearly universal, powerful solution. YT is already being run in line with some of our biggest simulations on blue waters, and it would love an architecture like this, right, with that second level of memory, because that's where you can do your analysis in line with the computation. So I think that's a building block. And then finally, the sharing. This is just, an FYI. This is not solving all problems, but there is a project that I'm involved in at SDSC called SeedMe, which is a software as a service thing that I think I think of it as Flickr plus YouTube for scientists. And the subtitle here is Your Results from Disk to Device. And by device, they mean what we carry around with us: smartphones, laptops, tablets. So what does it do? It is just a thing that can attach to anything you want. It's all Python based. It attaches to, in this case, a running simulation, and it is sending out tickers, which just gives status updates. And it is mediated by cloud services, and it's displayed in such a way that it's device agnostic. So you could be looking at this from your smartphone. This is all built into a collection. The user defines what a collection means. In this case, it's a collection of, it's a set of containers that are storing data items that are coming from 4 running simulations on Blue Waters. The void run, the rare peak, the normal region. So there's 4 simulations that are going on there, and it's sending out tickers, which I think of as tweets, except that, there's some ability for the user to attach metadata to these messages and have that sent. So that's a nice thing. If you are doing inline analysis with the simulation, it is producing data products like plots. And here, those are being put into these collections and cataloged. And you can just, from your device, whatever it is, you can check your collection and see what's in there. In this case, we've used YT to do a halo analysis of these protogalaxies and measure their stellar populations. And this is both POP2 and POP3 stars in these high redshift protogalaxies. And this is just served up, it's like you get an email, but it's your science. So I think this is an example of another building block for this, a better future where not only can we use these systems to do good science, we can get scientific analysis done along with that, and the results distributed to us, not just us, but anybody in our work group using web services over the internet. So I think we could be building some of these ideas into let me just say that, in the next HiPACC, there could be an infrastructure component to it, which isn't building your own infrastructure, it's leveraging the infrastructure that is appearing all around us and just focusing on the integration of that for specific needs within the UC astronomy community. And I think it could be done with very little cost because it's fundamentally a coordination effort. The development is happening, but is it coordinated? No. But if you coordinated the effort, you get so much more out of it, which is what the YT project has shown us. The talent is out there, the desire is out there. How do you coordinate that into something that's, useful, effective, cost-effective, and cool? So that's what I wanted to say about that. Any questions?